Good evening all. I am Harsha Gopalakrishnan, a research scholar from IIT Tirupati. So this is a live session for the NPTEL course Introduction to Abstract and Linear Algebra. This is a week 0 session which give you the basic idea about the course, and we will solve some basic problems. Every week you will have to solve and submit a set of problems which is called assignment problems. So we will solve a similar kind of problem every week, so that it will help you understanding the problem and solve the assignment problem. So let us begin today's sessions. Let me first share the screen. Are you all able to see the screen?
Yes, but not in full screen mode.
Are you able to see the screen?
Yes, but not in full screen mode.
Yeah. Okay. Is that fine now?
Yes.
Thank you. So, the first question is, what is said to be an ordered collection of objects? So, we have four options here. One is relation, function, set, proposition. Let us see what actually all these terms means. What is a relation? Relation. Let A and B are two sets. A, B are sets. We know that a Cartesian product of two sets A cross B. A cross B is defined as set of all element xy such that x in A and y in B. This is the Cartesian product A cross B. A relation can be seen as a subset of A cross B. R is a relation which is a subset of A cross B. So that an element xy in R, if xy is an element of R, we can say this x is related to y in some particular defined way. So, this is the basic definition of relation. Now, let us see what is a function. A function is also defined from a set A from a set B to a set B in such a way that for any x in A, we will have a element f of x, or we can call f of x equal to y, which is in set B. So, this is the function. This y will be unique for each x. Or we can say that this f can be seen as a subset of relation. That is, corresponding to each x in A, we have a y in B. So, it is also a form of subset of Cartesian product. So, function is a relation also. But conversely, a relation need not be a function always. Now, let us go to the next term, set. A set. Set is a well-defined collection of objects. See, if we are having, usually we will denote the set by capital letters, capital A, capital B and so on. For example, let us write A equal to set of all x, y, z. Here we are defining the set A.
Excuse me.
Yes.
Actually, the screen is not shared.
Okay, 1 minute. Is this okay now?
Yes.
Okay. Okay. this is an explicit definition of a set. Otherwise, we can define B. B is another set of all x such that 1 less than or equal to x less than or equal to 2. It is same as the closed interval 1, 2. Here we are not listing all the elements of the set, but we are defining how the set is defined. So, these all definitions are well defined. If such a definition means if we are able to find what are all the objects inside the set, inside the collection, we can say it is a set. For example, if we are just taking what are the top 10 actors in India, then it is not a set because it is not a well defined. So, I hope you understand what is a set. Next thing is proposition. Proposition means just a mathematical statement. Like, let us see, proposition, a mathematical statement. For example, if I am writing 1 less than 2, this is a mathematical statement. So, such statements are called a proposition. So, these are all the 4 terms given in the question. So, let us see. The question is what is a ordered collection of objects? From this it is clear that set is an ordered collection of objects. Here relation function, these are all defined as a subset with some properties and all. Proposition is a statement. So, we can say set is ordered collection means same as well defined collection of objects. So, set is an ordered collection of objects. Let us go to the next problem. Here the question is, a set of positive integers is either it is infinite or it is finite or empty or none of the above. So, let us see what are all these terms again means. What is finite? Finite set means if A is a set, if we are finding the cardinality of A, cardinality of A is denoted by mod A. If this is n for some positive integer n in z plus or z plus union 0, it can be 0 also. This is the, if this cardinality is n for some natural number, then the set A is a finite set. What it actually means is, if we can count the number of elements in the set, then it is a finite set. Otherwise, it is an infinite set. So, we don't have a particular number, means we don't know what exactly the number of the elements in the set. It may go to infinity. It can go to infinity. So, what is an empty set? Empty set is usually denoted by phi, or we can write in a empty curly notation. No elements in the set. So, such a condition is called empty set. So, we need to check whether the positive integers is infinite, finite or empty. Let us see what is positive integers. Positive integers we usually denote by z plus. Z plus equal to set of all 1, 2, 3, etc. This is the positive integers. Clearly, it is not finite because it is going infinity, 1, 2, 3, etc. and so and so. The cardinality is not finite, and also it is not empty. So many elements are inside this Z plus, so it is not empty. So we can say Z plus is an infinite set. Okay. So here the answer is set of positive integers is infinite. Now let us go to the next problem. For a symmetric matrix A, which of the following condition is true? So, what is the definition of the symmetric matrix? If A is a matrix, then and A equal to A transpose, then A is symmetric. See, from the definition itself, it is clear that for a symmetric metric A equal to A transpose. So option A is the correct answer. Now let us go to the other options also. Okay, I hope you know what is A transpose. Let us go to A transpose. If we are having a matrix A, then A transpose is the matrix such that the columns and rows of A are interchanged. That is, the columns of A will be the rows of A transpose and the rows of A will be the columns of A transpose. This is the transpose of A. For example, let's see A equal to 1, 2, 2, 3. Here A transpose is, we are interchanging the rows and column. So first row will become the first column. 1, 2 is the first row, it will become the first column. And second row is 2, 3, it will become the second column of A transpose. So here we can clearly see that A equal to A transpose. That is, all the corresponding entries are equal. So A equal to A transpose. So A is a symmetric metric. So for a symmetric matrix, they are asking whether all the diagonal elements are 1 or not. Let us see. Here in our example, we have diagonal elements 1 and 3. So it need not be 1 always. So this option B is false. And also A equal to minus A transpose. This is also not true. This condition is satisfied for a skew symmetric matrix. If A is skew symmetric, we can say A equal to minus A transpose. Now, next question is whether all the diagonal elements of symmetric matrix are 0 or not. So, again here the diagonal entries are not 0. So, it need not be 0 always. So, this fourth option is also false. Yeah. Now, the next question is, between 0 and 1, how many rational and irrational numbers are there? So, between 0 and 1 means, let us consider between 0 and 1 means it is a closed interval. Let us see it as a closed 0, 1. So, the question is how many rational, whether it is finite, infinite and so and so. Let us see. The first option is 0. That means there is only 1. There is no elements, there is no rational or irrational between 0 and 1, which is clearly not true, because 1 by 2 is an element of Q and 1 by 2 belongs to 0, 1. So, there is an element, so it is not 0. In the same way, in case of rational, if we are taking 1 by root 2, it is an element of irrational number and 1 by root 2 belongs to, it is in between 0 and 1. So, there exists at least one element between 0 and 1, both rational and irrational. So, next case is whether it is finite. Now, let us see. Take A as the set of all 1 by 2, 1 by 2 square, 1 by 2 cube, etc. etc. So, this is an infinite set. Also, each element in A is an element of Q, because it can be written in the form of m by n. So, A can be seen as a subset of Q, that is, A is a subset of rational numbers. A itself is an infinite set. So, Q should be an infinite set. So, this option B is false, because Q cannot be a finite set. In the same way, we need to check about irrational numbers also. What we got is Q is infinite. Now, we need to check whether Q complement is finite or infinite. Q complement. Q complement means set of all irrational numbers. We know that rational numbers are countable, and we can write closed 0, 1 as the closed 0, 1 intersection Q union closed 0, 1 intersection Q complement. What this means is, we are close to 0, 1 intersection Q means set of all rationals in 0, 1, and close to 0, 1 intersection Q complement means set of all irrationals in 0, 1. So, we are taking all rationals and irrationals in 0, 1, taking the union. So, it is all close to 0, 1. And we know that this set is a countable set. This is a subset of Q and Q is countable. So this set is a countable set. So what about this set? If this is also a countable set, then union of two countable set means a countable set. Then closed 0 1 will also be a countable set, which is not possible. Closed 0 1 is uncountable. So this closed 0 1 intersection Q complement should be uncountable. That means Q complement intersection closed 0 1 should be uncountable. Of course, an uncountable set cannot be a finite set. So this Q complement intersection closed to 0 1 should be an infinite set. Or in the alternatively we can say here we have A as a subset of Q, and we are considering an element 1 by root 2 in Q complement intersection close to 0 1, that is a irrational in 0 1, and we are multiplying this 1 by root 2 with each of the elements of A, then a rational into an irrational means it is an irrational. So we will get one set B as the 1 by 2 root 2, 1 by 2 square root 2, and so on. So this set is a subset of close to 0 1 intersection Q complement. So since this is an infinite set, we can say that set of all irrationals in 0 1 is also an infinite set. So here the answer is all the rationals and irrationals in 0 1 forms an infinite set. Now let's go to the next problem. What Z represents? This Z actually represents the set of all integers. Z equal to set of all integers. This is a standard notation in mathematics. And if we are writing Z plus, then Z plus is the set of all positive integers. And if we are considering Z minus, it is the set of all negative integers. So here the answer is Z represents the set of all integers. Now let us see what are all the notation for this rational, naturals and real numbers. So natural numbers is represented by n, like this. N is the set of all natural numbers. And rational numbers are denoted by Q. Q is the set of all rationals. And Q complement is the irrationals. And for real numbers we have the notation R. R with an extra line. Here all we have an extra line. This is the notation. R is the set of all real numbers. As explained in Z plus and Z minus, if we have R plus and R minus, we can say R plus is the set of all positive and R minus is the set of all negative real numbers. Now the question is, if S is the set given like this, then they are asking to write the S in explicit form. Now let us see how S is actually. S is defined as set of all X such that X is a letter in IIT NPTEL. So among all the four options, what is the S? That is the question. So we need to write each of the elements possible in S. That is, X should be a letter in IIT NPTEL. So the first letter of IIT NPTEL is I. So we will list this I here first. So the next letter is again I. So if we are adding I again, this is not needed. For a set, if an element is repeating, we don't need to list them again and again. That is, we just need to count them only once. So, if we have a repeating element, we will write only once, and second I is not needed. And we will find for the next letter, which is not I, that is T. Then the next letter is N, I, T, N. Next one is P. Again T is repeating, so we don't need to list it in the S. So the next non-repeating element is E, and then it is L. So these are all the distinct letters in the word IIT NPTEL. So we are just counting the listing the distinct letters. This is our set S. So in set we don't have any order, that is we can write in any manner the number of elements, the elements in the set we can write in any order. For example, I can write this S in the same way, like in a different way, like T, N, E, L, P, I. The only thing is I should list all the elements, I should not miss anything, but order can be anything. So from this option also we just need to check T, N, E, L, P, I. So A is the correct option. A contains all the letters in the word, and in B, C, D the problem is in B I is repeated twice, and here in C L is repeated twice, and D also I repeated twice. So these are all not the correct representation of the set S. Now the question is to find the power set of a set A. Here the set is A is given as A equal to closed set 1, 2. So B is the set of all subset of A. Set of all subset of A means the power set of A. We can denote B again as P of A. P of A means set of all power sets of B means the power set of A. That is, we need to find the subset. For any set A, empty set is a subset. So phi is the empty set notation. So phi is a subset. So phi is inside the set B. Now we will count the set which is having only one element. Set 1. Set 1 is a subset of set 1, 2, which is having only one element. Again set 2 we are considering. It is also a subset of 1, 2. Now one element set is over. So we will go to the two element set. Set 1, 2 is the only two element set, and this is same as A. So no more sets are here. So after that we cannot have no sets. So these are all the elements of B, that is B is the set of all phi, 1, 2 and 1, 2. So here in this option it is the option C, because 4 elements are listed. Also, if we are having a set A, and if cardinality of A is a set and cardinality of A is given as n, then the cardinality of power set of A will be 2 power n. So to check the answer, we can say here our cardinality of A is 2. So cardinality of power set, that is cardinality of B, should be 2 power 2, which is equal to 4, which is true because these are 4 elements we listed in B. So this is the power set or the set of all subsets of A. Now the next question is, we are given two sets S and T. So here also we need to find the explicit form of this set S and T. Let us see what is S. S is the set of all elements in the natural numbers such that x should satisfy the equation x square equal to 9. And then T is the set of all elements in the real numbers such that T should satisfy the condition x square equal to 9. Here in both cases the condition x square equal to 9 is same, but the thing is x from where x is coming. In the first set x should come from n, in the second set x should come from R. So in both cases the only thing is we need to solve the equation x square equal to 9. Let us see. X square equal to 9 means x equal to either plus 3 or x equal to minus 3. So if x equal to plus 3 or x equal to minus 3, these are the only two conditions such that x square equal to 9 is satisfied. Now we want to check whether this x belongs to S or T. So in order for this x belongs to S, x should belongs to n also. Here 3 belongs to n, but minus 3 does not belongs to n. So 3 is the only possible element that can be in the set S. So we got S equal to set 3. This is a singleton set. Now we are finding the T. T is given as set of all elements in R which satisfy x square equal to 9. So we have two elements 3 and minus 3 which satisfy x square equal to 9, and both 3 and minus 3 belongs to R also. So we can say T contains both minus 3 and plus 3. So our answer is S is singleton 3 and T is 3 minus 3. So option D is the correct answer here. Now let's go to the next problem. Here it is given Q is the set of all rationals and Q complement is the set of all irrational numbers. And the set minus A minus B is defined as set of all x such that which are in A but not in B. This is the A minus B. And we are asked to find the set R minus Q union Q complement. See, this Q union Q complement is actually equal to R, because every element in R is either a rational number or a irrational number. So R can be written as set of all rationals union set of all irrationals. So R minus Q union Q complement is R minus R. So by the definition of set minus, we can write R minus R as the set of all x such that x in R and x not in R. See, this condition is there is no x such that with this condition is satisfied. That is, there is no x with x belongs to R and x not belongs to R. What does this means? Means there is no element, it is an empty set. That is R minus Q union Q complement is an empty set. So here the option C is the right answer. All others are wrong. Now let's go to the next problem. We are having a matrix A here, which is an m by n matrix. A is an m by n matrix. So we can write A as A11, A12, etc. A1n, A21, A22, etc. A2n, etc. AM1, AM2, etc. AMN. This is the matrix A. In the same way, we can write B. B is an R by S matrix. So B will be B11, B12, etc. B1s, B21, B22, etc. B2s, BR1, BR2, etc. BRs. So if we are multiplying A and B, that is, we are doing A into B, what we are doing is we will take the first row and first row of A and first column of B, then multiply this row with this column. So that is the first entry of the A into B. That is, we will do A11 B11, A12 B21, etc. A1n BR1. So in order for this multiplication to be satisfied, the number of element in this row and the number of element in this column should be equal. So that means number of element in this row is n and the number of elements in this column is R. So So A into B is defined only if number of elements in only if n equal to R. So this is the condition for A into B to be defined. So here the option D is the correct answer. All other options are wrong. So these are all the week 0 assignments. So if you have any doubts, you can ask now. Yes.
Actually, I had a doubt in the very first slide,
Okay.
um,
I'll share the
where you
screen
were
also.
talking about, yeah.
So first page you are talking, right?
Hmm.
Yeah.
So relation is also a subset of relation is also a set basically. So won't that definition? I mean, then won't relation also be an answer for this question?
No, this is asking for a general definition. What is an ordered collection of objects? It can be any object. But relation means if we are having two sets, then it is a subset of the Cartesian product. It is not any ordered collection of objects. For example, if I am taking set x, y, z, it is not a relation, right? But it is a collection of objects. It's a well-defined collection of objects.
Okay,
Is that clear?
got it. Yeah, yeah. Thank you.
Yeah, thank you. Any other question?
No.
Yeah, okay. Okay, now we will go to some more basic concepts like some kinds of relations, some kinds of functions, and so on. We have different kinds of relations on a set, on a particular set, such as reflexive relation, symmetric relation, transitive relation, anti-symmetric, and so on. Here we will check what is reflexive relation, symmetric relation, and transitive relation, because these three relations together forms an equivalence relations. The question here is to check whether the relation given RST are either reflexive, symmetric, or transitive. So before going to the question, let us see what is a reflexive relation, a symmetric relation, and a transitive relation. Let A be a set and R be a relation on A. That means R is a subset of the Cartesian product across A. Then R is said to be a reflexive relation if for every A in A, we have A belongs to R. A should be in R for all A in R, for all A in A. So, if such a condition is satisfied, we will say the relation R is a reflexive relation. Let us see one example. We are taking the set A as set of all x, y, z. Let R equal to set of all xx and xy. So is this a reflexive relation? First question is this reflexive? No, because the condition for reflexivity is corresponding to each A in A should belongs to R. That means XX should be in R, YY should be in R, and ZZ should be in R. That is, if we are taking R1 as the set XX, YY and ZZ, then this R1 is a reflexive relation, and this is the least possible reflexive relation. That is, these three elements is the minimum required things in the reflexive relation. So if we are adding one or two more elements in R1, say XY and XZ and so on, so then also it will remain a reflexive relation, because the only condition is we need AA should be in R for all A in A. That is satisfied in R1. So R1 is a reflexive relation. Now we will see what is a symmetric relation means. Here also a set and a relation R on A. Again, R is a subset of A cross A. Is symmetric when will it said to be symmetric? If we have element xy in A, then yx should be in, if xy is in R, yx should be in R. That is, this condition should be an if and only if condition. So whenever we have an xy in R, then yx should be in R. Conversely, if yx is in R, then xy should be in R, where xy are elements of A. If this condition is satisfied, then R is a symmetric relation on A. Again, we are taking set A, one example, phase 1, 2, 3. We are taking A equal to 1, 2, 3 and R equal to set 1, 2, set 2, 2, set 2, 1. Now see, 1, 2 is there, 2, 1 is there, 2, 2 is there, 2, 2 is there. So all the conditions of the symmetric relation is satisfied here. So clearly R is a symmetric relation. Now if I am taking R1 and another relation as 2, 2, 3, 3, 3, 1. Clearly it is not a symmetric relation, because 1, 3 is not in the relation R1. So it is not a symmetric relation. Now the third kind of relation is transitive. A relation R on set A. So this R is said to be a transitive. It is transitive if we have xy and yz in R, then the element xz should be in R. Then xz is in R. If this condition is satisfied, then it is said to be, then R is said to be a transitive relation. Now let us see one simple example again here for the transitivity condition. Suppose A is the set 1, 2, 3 and I am taking the relation R as set 1, 2, set 2, 3. Then in order for R to be a transitive relation, since 1, 2 and 2, 3 are there, 1, 3 should be there, right? Now let us see, this is a transitive relation. This is clearly a transitive relation, right? Now an example, S equal to 1, 2, 2 1 2 3. This is not a transitive relation because 1 2 is there, 2 1 is there, but 1 1 is not there. So this is not a transitive relation. So these are the three relations: reflexive, symmetric and transitive. Now our question is to check whether the relations given in the set A equal to 1 2 3 4, whether these are STR, reflexive, symmetric or transitive. Now let us see the first one. First we will check the reflexivity of R. In order to be R to be a reflexive, we need 1 1, 2 2, 3 3 and 4 4 should be in R. But we can see 2 2 is not here in R and 4 4 is not here in R. Therefore, R is clearly not reflexive. R is not reflexive. Now let us check the symmetry condition. Clearly we can see 2 1 is an element in R, but 1 2 is not an element of R. That implies it is not symmetric. Now the third condition is transitivity. Here let us see this 3 2 and 2 1 are elements of R, but 3 1 is not an element of R. That is not transitive also. So R is not transitive. The reason is 3 2 and 2 1 belongs to R, but 3 1 does not belongs to R. Why it is not reflexive? For example, we can say 2 2 does not belongs to R, and not symmetric means because two 1 belongs to R, but 1 2 does not belongs to R. Okay. Now let us go to the next problem, second one. Here given S is 1 1, 2 2, 3 1, 3 3, 4 2, 4 4. See, here we can see 1 1 is there, 2 2, 3 3, 4 4 all are there. So clearly S is reflexive. S reflexive. Now whether it is symmetric or not, let us see. Here 3 1 is there in the S, but 1 3 is not there in S. So S is not symmetric. S is not symmetric. Because 3 1 in S, 1 3 does not belongs to S. Now one more condition we need to check is transitivity. So by inspection we can check whether it is transitive. For example, we will see 1 1 is there, 2 2 is there, like that. See, 3 1 is there and 1 1 is there, 3 1 is again there, and 3 3 is there, 3 1 is there, 3 1 is again there, 4 2 is there, 2 4 is there, 4 2 is there, 4 4 is there, 4 2 is there, again 4 2 is there. That means all the possibilities, like that, all the possibilities we can check. By inspection itself we can say S is a transitive relation. S is a transitive relation. Now we have one more example to check. The third one, T is 1 2 1 1 2 1. From the inspection itself we know that it is not reflexive because 2 2, 3 3, 4 4 are not in T. So T is not reflexive. And about the symmetric condition, we have 1 2 is there, 2 1 is there, and 1 1 is there, 1 1 is there, means T is a symmetric relation. Now the case of transitivity, 1 1 is there, 1 2 is there, 1 2 is there, but 2 1 is there, 1 2 is there, 2 2 is not there, right? So this says that this T is not transitive relation. T is not transitive. The reason is 2 1 1 2 are there, 2 1 1 2 are in T, but 2 2 is not in T. So we have examined all the cases of this example, that is whether R, S, T are reflexive, symmetric or transitive. Now let us see what is an equivalence relation. A relation R on a set A is said to be equivalence relation if it is reflexive, symmetric and transitive. So what actually equivalence relation means? It should be a relation R should be reflexive, symmetric and transitive. If such a condition is satisfied, then we can say that R is a reflexive relation. So let me give one simple example for the equivalence relation. Let A is the set 1 2 3 and R equals set 1 1 2 2 3 3. Clearly it is an equivalence relation. R is an equivalence relation. For that it is easy to check whether it is reflexive, symmetric and transitive. It is a one trivial example. Okay, now we have already talked about a function. What is a function? Now let us go to the function and two different kinds of function, say one-one function and onto function. Let A, B are sets. A map F from A to B is said to be a function if for x an element of A there exists unique f of x in B. That is, it is an association from the set A to the set B. That is, corresponding to each A in A, we should have a unique element f of x in B. Usually we call this f of x as the y, the image of f, we usually call it as y. Now functions are, let us see two different kinds of function, one-one function and onto function. Let us see what is one-to-one function. Suppose f is a function from A to B, then it is a one-to-one function. F is one-to-one function if different elements in A have different images. That is, if f of x1 equals f of x2 implies x1 should be equal to x2. That is, if x1 and x2 are different, then f of x1 and f of x2 are or we can alternatively say x1 and x2 are different, then f of x1 and f of x2 are different, that is different elements in A maps to different images. This is the example of one-to-one function. Now let us see what is a non-to function. Again, f is a map from A to B, then f is on to if corresponding to each element in B, say corresponding to each y in B, we are denoting the elements of B by y, there should exist an x in A such that f of x equal to y. That means corresponding to each element in B, there should be an element in A such that that map is mapping to this element of B. This is the on-to function. Now what is bijective function? If f is both 1, 1 and on-to, then f is bijective function. That is, this is the definition of bijective function. If it is 1, 1 and on-to, it is bijective. Otherwise, if it is bijective, then it should be 1, 1 and on-to. And also, if we are able to find a map from A to B, a function which is a bijective function from A to B, then we will say there is a 1, 1 correspondence between A and B. If there exists a bijective map from A to B, then there is a 1, 1 correspondence between A and B. Okay. So now let us see some example for 1, 1 on 2 bijective maps, and then let us see examples. First of all, take a map F from set of all integers Z to set of all integers Z. It is defined as f of x equal to x plus 1. So let us see whether it is a 1, 1 on-to map. First condition is first, in order to check the 1, 1 condition, we need to find f of x1 equal to x2, whether x1 equal to x2 or not. By definition of f of x1 equal to f of x2 means x1 plus 1 equal to x2 plus 1, and this clearly implies x1 equal to x2. So this f is 1, 1 map. Now we need to check whether f is on-to or not. For that, corresponding to each element in Z, say y is an element of Z, we should have an element of Z such that that element is mapped to y. So let y in Z, take y minus 1 in Z. Clearly y in Z, y minus 1 is also an element of Z. Then check what is f of y minus 1. So this f of y minus 1 by definition will be y minus 1 plus 1 equal to y. That is for y in Z, this y corresponding to y in Z, we have an element y minus 1 such that f of y minus 1 is mapped to y. So we can say it is f is a on-to map also. So it is a 1, 1 on-to map and it is a bijection. Now let us see another example. We are taking f from R to R defined by f of x equal to x square. First we need to check f of x1 equal to f of x2, then x1 equal to x2 or not. This is our question first, right, in order to check the 1-1 condition. Or alternatively, we need to check x1 not equal to x2 should imply f of x1 not equal to f of x2. Take 1 and -1 in R. Clearly 1 not equal to -1, but f of 1 equal to 1, which is same as f of -1. That implies different images, that is different images 1 and -1 is having same image 1 in R, which shows that f is not a 1-to-1 map. F is not 1-to-1, right. Now we will check the onto condition of f. We know that f is a map from R to R defined by f of x equal to x square, but we know that x square is always positive, always a positive number. So if we are taking a negative number from R, say -1, then it is not having a pre-image in R. No negative number in R have a pre-image under the map F, right. So we can say F is not onto. Okay. So we will see two more examples in which one the function f is 1-1 but not onto, conversely onto but not 1-1. So let us see the third example. Take f map from Z to Z such that f of x equal to x. First of all, for the 1-1 condition, we will check f of x1 equal to f of x2. That implies 2x1 equal to 2x2, which implies x1 equal to x2. This clearly implies f is a 1-to-1 map. Now we need to check whether f is onto or not. So we are taking, let y is a element of z, because f is a map from z to z. Corresponding to each y in z, we should have a pre-image here. Suppose it is having a pre-image here, that is suppose there exists x in z such that f of x equal to y. That implies, by definition, f of x is 2x. 2x equal to y. That implies x should be equal to y by 2. So if corresponding to each y in z, if there exists a pre-image, that pre-image will be y by 2. So let me take y equal to 2, y equal to 3. 3 is an element of z. Then the possible pre-image of y is x equal to y by 2, which is equal to 3 by 2, which does not belongs to z, but the map f is defined from z to z. So there is no pre-image for y equal to 3. Which shows that this f is not an onto map, right? Okay. Now let us see one more example. Suppose f is a map from -1-1 to closed 0-1, defined by f of x equal to mod x. We need to check whether f is 1-1 or onto. Consider 1 and -1. These 1 and -1 are distinct elements. which belongs to minus 1, 1. 1 not equal to minus 1, but we know that f of 1 equal to f of minus 1. Both are the modulus value of 1 and minus 1, which is 1, which implies that f is not a 1-1 map. Now we will see whether it is onto or not. So it is very easy to check if is an onto map, because corresponding to each element 0 in 1, we can say 0 1 map 0 1 in the minus 1 1 map to 0 1. That is, for each x in 0 1, x belongs to minus 1 1 and f of x equal to x, right? Such a condition is satisfied. So f is an onto map. F is onto. So here we have one example which is not a one-to-one map, but it is a onto map. So this is about the functions. Now let us go to one more example. Here it is about an equivalence relation. We already talked what is an equivalence relation. Here we need to prove that less than on the set of integers is not an equivalence relation. Here less than is a usual less than. This is a very simple thing. Let us see. For example, here less than is the relation. So 1 1. 1 1 is not in the relation less than, because 1 is not strictly less than 1. This less than relation means if x is strictly less than y, let us write what less than means. R equal to, if x strictly less than y, then xy belongs to less than relation. Here 1 not strictly less than 1, so 1 1 does not belongs to the relation less than. That is, here 1 1 is not belongs to the less than relation, because 1 not less than or equal to not less than 1. So from this condition itself it is not symmetric, so we can say it is not a reflexive, not an equivalence relation. That implies it is not an equivalence relation. So in the same way you can check whether it is anti-symmetric, whether it is symmetric or transitive and so on. For symmetric also we can say if 1 less than 2, then 2 should be less than 1. This is not the case, right? So it should not be symmetric also, but it will be a transitive relation. Anyhow, it is not an equivalence relation. Yeah, so it is all about the class, and let me stop the sharing now. Yeah, okay. So if you have any doubt, you can post your doubts in the discussion forums, which is in the NPTEL site in the course Introduction to Abstract and Linear Algebra. So this is all about the week 0 session, and in the next week again Monday from 6 to 7 p.m. We will meet in the same link. So thank you everyone for attending, and we will see you on the next week.